Hi, in 10.6 we're looking at parametric equations. So in the rectangular coordinate system we want to graph curves using equations involving the x and y. But in applications like when you're tracking the motion of an object over time or like planets, it's useful to introduce a third variable called the parameter. So we're going to parameterize a variable. All right, so a system of parametric equations is a pair of functions, x of t and y of t, where t is a parameter. Most of the time it would be time. Parameter, and I'll just call it time, because in most applications that's what it is. As t varies over an interval, the set of ordered pairs x of t and y of t are going to trace out a plane curve. All right, the direction of which the curve is traced as t increases is called the orientation of the curve. Okay, let's continue. So we're going to parameterize a curve. When we define a curve using parametric equations, it's called parameterizing it. So that's what we're going to do. We're going to parameterize an equation using the parameter t. All right, so it's going to describe not just the path, but also the direction in which the path is being formed. So in the first example, they're asking us to construct a table of values and sketch the graph for the parametric equations. So they give us a pair, x of t and y of t, and they give us the domain for t. So t can be from -2 to +2. So let's go ahead and start our table. So our table is going to consist of x values, y values, and t values. Let's actually put the t first. So we'll start with the t value, x and y. Okay, and they tell you what t should go from. It goes from -2 to +2, so we'll go -2, -1, 0, 1, 2. All right, so all you got to do is substitute those values into the x of t and the y of t equations, and that'll give you the coordinates for the x and y. So I'm going to go ahead and fill this out, and you should get the same, but you should work on this on your own and then compare your values with my values. Okay, once you have those points plotted, the table complete, now we can plot the points. So the first point will be 3, -4, which would be down here. And then we got 0, -2, and then -1, 0, and then 0, 2, and then 3, 4. Okay, connect those points with the nice smooth curve. And also, we draw arrows to indicate the orientation or the direction in which the curve is being traced. And it starts from the bottom and it starts moving up. So that's a parametric, or that's called a plane curve. Okay. Another useful thing to do is to rewrite is to actually eliminate the parameter t and to write the equation in Cartesian form. So that's another thing that we can do, and we will do that on the next page. All right, so that's going to involve algebraic substitution. So you solve one equation for t and you substitute it into the other. So we're going to solve for t for one of them, one of the two equations, and then substitute it into the other equation. When there's trig functions involved, what you're going to want to do is you're going to want to use this identity, the Pythagorean identity, sine squared plus cosine squared is equal to 1, and that'll help us eliminate the parameter t. So let's look at this first example. Eliminate the parameter to find the Cartesian equation for these sets of parametric equations. So first figure out which one looks easier to solve for. Does this t look easier to solve for, or this one? I would definitely go with this one because it doesn't have the square. So let's go ahead and solve for t for the y equation. So we'll start there. We'll solve for t. Whoops, that's not what I wanted to do. I wanted to do this. Solve for t. Okay, so we have y equals 5 minus t. You should end up with t equals 5 minus y if you add t over and then subtract y over. You would get this. So this is what we're going to substitute into the other equation. So now we take the x equation, and instead of t, we're going to substitute it with 5 minus y. Don't forget the square, and then the plus 6. So I'm just writing out the x equals equation, but in the place of the t, I'm replacing it with 5 minus y. And actually, that's as far as you need to go. If you want to, you can go ahead and expand this out, distribute the two, combine like terms. So if you do all that, if you choose to go that far or farther, the next step, if you'd like to, you can either enter the answer as you see it here, or you can continue to expand and combine like terms, and you will get x equals 2y squared minus 20y plus 56. But that's an optional step. You really don't have to go that far. You can just leave your answer like this if you would like. So both answers are acceptable. Okay, let's continue. Let's try another one of these problems where we're eliminating the parameter, but let's try one that involves trig functions. So here's what they say. You want to isolate the trig function and then use a Pythagorean identity. So step one is to isolate the cosine or the sine, and the sine, square both sides of the equation, and then you can add those equations together and use the identity, the famous identity, sine squared plus cosine squared is equal to 1. Okay, so let's start with the x equation. X equals 4 cosine t. To isolate the cosine, you would divide both sides by 4. And now we have cosine of t is equal to x over 4. And now what we want to do is we want to square both sides of the equation so that we can use the identity. So let's square both sides. And now that's going to give us cosine squared is equal to x squared plus 16. Okay, we do the same exact thing for the other equation, y equals 3 sine t. Isolate the sine by dividing both sides by 3. Sine t equals y over 3. And then we square both sides of the equation. And once again, we're squaring both sides because we want to be able to apply the Pythagorean identity. You can't apply it unless you have sine squared plus cosine squared. Okay, so now that we have sine squared and cosine squared, now we can add those. So if you add those two together, x squared plus 16, x squared over 16 plus y squared over 9, that's the Pythagorean identity because we're adding sine squared and cosine squared together, which gives you 1. So this should equal 1. All right. If you were to graph that, that is the equation of an ellipse. You could go ahead and use Desmos.com if you want, and you would see it is an ellipse. Okay, let's continue on to the next page. So this time we're going to find parametric equations from rectangular equations. Okay, so let's see what they ask us to do. So we can convert any Cartesian equation into a set of parametric equations by just doing the simple method here. You just let x of t equal to t, and then you just substitute that into the y equation. So, all right, so let's look at an example here. So if you have the equation y is equal to x squared minus 3, and you want to let x of t equals t, this is the easiest thing you can do to parameterize the equations. You just let x of t equal to t, and then all you have to do is substitute t for x, and you're done. So that's going to be y of t would be t squared minus 3. It really is that simple. But there's infinitely many things you can call x. You can call x, instead of just t, you can call x t plus 1. So that's what they do in this example. So if you let x of t be t plus 1, then you just replace the x with t plus 1, and then you end up with t plus 1 squared minus 3. Or you can do plus 2, t plus 2, t plus 3, t plus 4, etc. So there are infinitely many ways you can do this. So that's what they say here. There are infinitely many ways to do this, but the most simplest way to do it is just simply let x of t equal to t. So that's what I would recommend you do. For this following exercise, they're asking us to find two different sets. So let's do exactly what they did. For the first set, we'll let x of t equal t, and for the second set, we'll let x of t equal t plus 1. So let's start with the first set. Let's let x of t equal t. If we do that, then the y of t parametric equation becomes, instead of x plus 2, it becomes t plus 2 to the second power plus 1. So that is our first set of parametric equations. It's really pretty simple. As you can see, you're just replacing the x with the t. All right, now let's try a different set. Let's do what they did up there in the notes. They let x of t be t plus 1 for the second set. So now we're going to have y of t is equal to t plus 1 plus 2 to the second plus 1. So notice I'm just plugging in, I'm replacing the x here with t plus 1. And so that's why I'm getting t plus 1 plus 2. But now we can combine these like terms, and our final answer will simply be y of t is equal to t plus 3 quantity squared plus 1. And that is how you would parameterize a Cartesian equation. Okay, let's see if there's anything else for us to do. I believe we have one more problem down below. All right, so looking at applications of parametric equations, like I mentioned earlier, they can be used to model projectile motion, planetary orbits, and other time-dependent paths. All right, so here for this example, they say an object travels along a straight path from -5, 3 to 3, -1 in 4 seconds. Find the parametric equations for the position of the object. Well, they do say that it is a straight path, so that means we're looking at a straight line here. So we can write a Cartesian equation, since we know how to find the slope of between 2 points, and we can also find the y equals mx plus b line. So let's do that. Let's go y equals mx plus b. That's the equation of a line. All right. And we also know that the range or the domain of t is going to be between 0 and 4 seconds. Because that's what they say here, in 4 seconds. All right. So first things first, let's find the slope of the line that crosses those 2 points. So here's the slope formula. So m is equal to y2 minus y1 over x2 minus x1. Here's your x1, y1, x2, y2. So now let's find our slope. We're going to have -1 minus 3 over 3 minus -5. Careful with those double negatives. You should get -4/8, which is -1/2. All right, double check that. So we got the slope of the line. Once you get the slope, now it's time to find the b, which is the y-intercept. So in order to find the y-intercept of a line, let's first plug in the slope into the equation, the slope-intercept form. So we have y equals -1/2 x plus b. I simply replace the m with -1/2 because that's what the formula gave us, -1/2. Now it's time to find the b, which is the y-intercept. To find the y-intercept, you can choose either one of the 2 points. It doesn't matter which one. Substitute x. I'm going to choose the second point. So I'm going to substitute 3 for x, -1 for y, and then that's going to allow me to solve for b. So let's do that now. So y is -1, x is 3. If you solve for b, you're going to get -1 equals -3/2 plus b. -1 is the same thing as -2/2. That's the same thing as -1. The reason I'm changing that is so that I can add 3/2 to both sides. And when you do that, that's going to give you b equals +1/2. Okay. Now that you have the y-intercept, now we can write our equation as y equals -1/2 x plus 1/2. Now we have to parameterize it, because remember it says here, find the parametric equations for the position of the object. So we found the Cartesian equation, but that's not what they want. They want the parametric equations. So we just do what we did just in the previous example. You parameterize the equation, and let's do that by calling let x of t be t, and y of t will then become -1/2 t plus 1/2. And that's it. We are done with this problem. So those are the parametric equations for the path of that object. And that completes this section.